So in this video, we will look at a few problems from Euclidean geometry. These problems come from past papers. I will do as many as I can for the duration of this video. So here's the first one. Question 9.1 says, in the diagram, A, B, C, D is a cyclic quadrilateral. O is the center of the circle. So we have to use this diagram above to prove the theorem, which states that the opposite angles of a cyclic quadrilateral add up to 180 degrees. In other words, we must prove that B plus D is equal to 180 degrees. So B plus D. Often in Euclidean geometry, when we are about to do proofs, we have to perform certain constructions so that it is easy for us to prove. And in this case, the construction we will perform is to draw a radius from point A to the center, and from another one from point C to the center. The aim is not to use the radii, but it's to partition O into O1 and O2. Then we use the theorems that come before this theorem of cyclic quads. One of the theorems that comes before this is the one that says the angle at the center is twice that at the circumference, and that is the one we are going to use. But to write this down, we will say construct, or we will say construction, and then we will say join A to O and C to O such that we form O1 and O2. And then now we can start using the theorems. O1 is an angle at center, which is supposed to be twice this angle on the circumference, B. So O1 is going to be 2 times B. And your reason is angle at center equals 2 times angle at circumference. And then O2 will also be an angle at the center. However, it's going to be equal to twice the angle D instead of the B. So this is going to be 2 times D. And the reason is the same. Angle at center equals 2 times angle at circumference. Write it out completely. Now, if I am to add these two angles, I will form a revolution. So O1 plus O2 should be equal to 360. So we can say angles around a point, or you can say angles in a revolution. But we know that O1 is 2B, and we know that O2 is 2D, and this is 360. We can divide everywhere by 2, and and we will therefore get B plus D being equal to 180 degrees. We have now proven the theorem that we are asked to prove. So you can end the proof. Let's move on to the next one. We've got 9.2 here. It says, in the diagram, O is the center of the circle with a reflex angle of 230 degrees. Now, if this reflex angle is 230 degrees, make sure you understand that this reflex angle is twice S and not twice Q, okay? O1 is the one that is twice angle Q. So make sure that makes sense to you. So P, Q, R, and S are points on the circumference of the circle with chord SR extended to point T, and then QRT is 85, OPS is 20. Now clearly we can see that this is a cyclic quad, so all the theorems of a cyclic quad apply here. So the opposite angles of a cyclic quad are supplementary. The exterior angle of the cyclic quad is equal to the interior opposite. So we might have to use that. So in the first one, they are asking for angle S. And clearly, since we have this reflex angle 230 degrees, that one is going to be 2 times S, meaning that S is half of this angle here. So S is going to be 1 over 2 times 230, which should give you 115 degrees. And this is because angle at center equals 2 times angle at circumference. So we are done with this. So this is 115 degrees. But Q now, which is the next question, is the opposite to S. We know that Q plus S, this should be equal to 180 degrees. And the reason for this is opposite angles of a cyclic quad. So what does this mean? It means Q is 180 minus S, which is minus 115. And that gives us 65. And then lastly, we've got P1. P1 is this angle here. P is opposite angle R. Angle R happens to have an exterior angle, which is 85. So P1, by the way, this is 921 and this is 922. So 923 would be knowing that P1 plus the 20 degrees, so that is the whole of angle P, is equal to angle R, is equal to 85 degrees, the angle R that we are given. So the reason for this is exterior angle of a cyclic quad. So P1 should be 65, I presume. And then we are done with question 9.2. So we are on question 9.3 now. Let's see. We are told that in the diagram PQRS is a cyclic quadrilateral. So all the laws or the theorems of cyclic quads apply. Opposite angles are supplementary, and the exterior angle of a cyclic quad is equal to the interior opposite, or the opposite interior angle. So they say here QA intersects SR. Here's QA, which intersects SR at point A, and then SAQ is 130 degrees, meaning that this A is going to be about 50 degrees, right, to make the angles on a straight line 180. So, and they tell us that AQR is 20 degrees. They are looking for the size of P with reasons. So we know that P plus R should give us 180 degrees. So if it's possible to find R, that is what we must do. So we could use angles, the exterior angle of a triangle. If you look at triangle AQR, this 130 degrees is the exterior angle. So R plus 20 degrees, R plus this part of Q is actually going to be equal to 130 degrees because of the exterior angle of a triangle this time. But you are free to first find A1, and then after finding A1, use the sum of angles to find R. I'm just doing the shorter version of it. So this is going to be 130 minus 20, which is 110 degrees. So P plus R, like we had said, is equal to 180 degrees. And that is opposite angles of a cyclic quad. And this is now going to be P is 180 minus 110, which should give us 70 degrees. So that is P. Let's move on. Okay, we've got another proof here. Question 8, they say in the diagram below, DA is a tangent to the circle. They want us to prove the tan chord theorem in this case. Use the diagram below to prove that the theorem that states that DAB, which is this angle, is equal to BCA, which is that angle. So that is tan chord theorem. I said earlier, often when we do proofs in Euclidean geometry, we first construct. So let's perform a construction. We will construct like this. You can call this part L, it's up to you. You can call it whatever you want. But the aim of this construction was so that we partition A into A1 and A2, and partition C into C1 and C2. That was the entire aim, right? Our goal is to prove that A1 is equal to C1. So let us kind of start. The construction, what we are going to say in the construction, construct AL such that it is a diameter then join L to C. You can add on and say label A1, A2, and C1, C2. So let's just add it. Label A1, A2, C1, and C2. Okay? Because that was all part of our construction. Now, if you're looking at LB subtends C2 at the circumference. It subtends this angle here, that is LB, the arc or the segment, and also the same segment LB subtends A2 here. So we can start talking about that. C2, or rather let's start with A. A2 is equal to C2 because these are angles in the same segment. They are subtended in the same segment. So another thing we should note, since we said we are constructing AL such that it is a diameter, it means that this is going to be a 90 degrees. Also, this is going to be a 90 degrees. Because if this is a diameter, there's a theorem that says that diameter is perpendicular to radius. To tangent, tan perpendicular to diameter. And there's a theorem that says that a diameter subtends a 90 degrees at the circumference. And that is what we are using here. So I'm going to use this red color to write those things down. So A1 plus A2, which is the angle formed by the diameter and the tangent, is equal to 90 degrees. Why? Because of tan perpendicular to diameter. We can try to simplify. We are looking for A1 here, so we can say A1 is equal to 90 minus A2 and leave it like that. And then we can also talk about C1 and C2. C1 plus C2 also equals to 90. It's subtended by a diameter, so we say these are angles in a semicircle. And we can make C1 the subject of the formula again, because we said we are trying to compare A1 to C1. So C1 is going to be 90 minus C2. But remind yourself, we said A2 and C2 are equal to each other. So we can go ahead and say this is 90 minus A2 instead. Now C1 is 90 minus A2. Also A1 is 90 minus A2. This therefore means that A1 is equal to C1. They are both equal to 90 minus A2. And you can make the conclusion that they wanted us to prove DAB is equal to BCA. And we have now proven the theorem. Okay. We move along to an 8.2. So here they say in the diagram below, O is the center of the circle, QPRU. OQR is equal to 17 degrees and QRU is 51. So since O is the center of the circle, just know that every line from the center to the circumference is equal to one another. Okay, so you will realize that P2 is going to be equal to Q1 because this is an isosceles triangle, right? Just keep in mind those kind of things. But since we do have angles that are subtended at the center, like O1, O1 will be equal to 2 times R, and even O2 will actually be equal to 2 times P2 because O2 is subtended by the arc UQ, and UQ also subtends P2 at the circumference. So O2 is twice P2, O1 is twice R1. Just keep that in mind. They want us to calculate with reasons the sizes of the following angles. So like we already said, this is R1. Another thing we shouldn't forget is that since O is a diameter, and O is the center, and UP is a straight line, that means UP is a diameter. And if UP is a diameter, then we've got a 90 degrees there. So that is the first thing we are going to do in order to find R1. We will tell ourselves that PRU is equal to 90 degrees, and this is because of angles in the semicircle. So this will therefore mean that R1 is equal to 90 minus 51 because PRU is the same thing as R1 plus 51. So if I take the 51 to the other side, I think we are supposed to get something like 39 degrees. Okay, and that is our R1. R1 is 39. If we have R1 as 39, then we can easily find O1 because O1 is twice of R1. So O1 is going to be 2 times R1, and the reason for that is angle at center equals 2 times angle at circumference. So this is going to be 2 times 39. 39, that's 18 plus 60, which should be 78 degrees. So that is our O1. Now that I know O1, it is easy to even find O2 because these are angles on a straight line. That is if we have a reason to find O2. The next question they are asking is for Q1. Remember, OP and OQ, sorry, these are equal to each other. This means that the P2 is going to be equal to Q1. Sorry about that. So it means P2 is going to be equal to Q1. So the full thing, so we can decide to call either one by the other. So instead of saying P2, we can call both of them Q1. So this means that Q1 plus Q1, in other words, Q1 plus P2, plus O1, which is 78, should be equal to 180 degrees because this is the sum of angles in a triangle, right? But I think it's important to first state that P2 is equal to Q1. And let me try to bring all of this a little bit lower. P2 is equal to Q1, and this is because these are angles opposite equal sides. So using the sum of angles, we've got 2Q1 being equal to 180 minus 78, which I think is 102. If you divide by 2 both sides, Q1 should give you a 51 degrees. And that is our Q1 and P2. That is 51. Now, if this is 51 and they're asking for U2, U1 is subtended by the chord RP. But the same chord RP subtends this whole angle Q. These are angles in the same segment, U1 and the angle Q. So U1 is equal to Q, which is equal to 51 plus 17. I've said these are angles in the same segment. So this is 68, I suppose. And that is it. We are done with 8.2. And then we've got this question 7 here. Also one of the easier questions. So in the diagram below, O is the center of the circle. SR is equal to 40 centimeters. And OT is perpendicular to SR. Now we are given, this takes us to theorem 1. We are given a line from center that is already perpendicular to the chord. So what happens to the chord? The chord is bisected. So we say line from center perpendicular to chord bisects the chord. So SU is equal to UR, but they are telling us that SR is 40. So each of these are going to be 20. It is also given that UT is equal to X and OU is 2X. So OU is 2X, UT is X. So this is easy enough for us because we know that OT is a radius, but also OR is a radius. So if we are ever asked OR, it should be equal to OU plus UT, which is the same thing as 3X. And guess what? We are asked for OR. OR in terms of X is equal to 3X. Now they are asking for the value of X, leaving your answer in simplest surd form. So let's start by saying UR is equal to SU, which is equal to 40 divided by 2, which is 20. And the reason for this is line from center perpendicular to chord. Right? Now that we know that UR is 20 centimeters and we know that OU is 2X, we know that OR is 3X, we can now use Pythagoras theorem. OR squared is equal to OU squared plus UR squared. This is Pythagoras. Because of this, we can now substitute. OR is 3X squared, which is equal to OU, which is 2X squared, and then the 20 squared. This is 9x squared, 4x squared, and then 400 this side. Let's collect like terms. 4x to the other side gives us 5x squared is equal to 400. You can divide both sides by 5. So what are we given? X squared is equal to 400 divided by 5. What is that? 20 divided by 5 would have been 4. Okay, 400 divided by 5 should be 80. And then if you take the square root, it's a plus or minus, but we will obviously take the positive square root of 80, and that should give us, let's see, 80 is same thing as 2 times 40. 40 is the same, okay, or it's the same thing as 4 times 20. I'm just trying to figure out the third form because that is what they asked for. So 80 is the same thing as 4 times 20. The square root of 4 is 2, so this is 2 root 20, but 20 is the same thing as 4 times 5. So the square root of 4 is another 2, so this is gonna be 4 root 5 units, or rather centimeters, because the answer was in centimeters. So that is the answer for X. We've got question 7.2. So they say in the diagram below, O is the center of the circle. A, B, C, D are points on the circumference of the circle. OD is parallel to AB. And so whenever we have parallel lines, we can now think of the alternating, corresponding, and co-interior angles. And OBA is equal to 54. So clearly, because these lines are parallel, this 54 for OBA is going to be equal to this, to O2. So we can expect that, O1 forms a Z, it forms alternating angles. O1 is going to be 54. If O1 is 54 and O1 happens to be subtended by DB, DB also subtends A2 at the circumference. Follow DB and see where it goes to the circumference. It subtends O2. O2 is going to be half of O. So that's going to be 54 divided by 2, which should be 27, I think. And then that is if we are looking for A2. What else might we look for? Pay attention. ADCB is a cyclic quad, even if it doesn't look like that. We've got 4 points in a closed diagram that are connected or that are touching the circumference. So ADCB is a cyclic quad. So it means A2 is equal to C. So when we are looking for C, we will just, it won't be equal. A2 plus C will be equal to 180. So when we are looking for C, it's just going to be 180 minus A2. And then, yeah, let's try to answer these questions. So, like expected, we are asked to calculate A2. So 721. To find A2, I propose that A2 is half of O1. So we have to first find O1. So O1 is equal to OBA, which is equal to 54 degrees. These are alternating angles. And whenever you're using these theorems of parallel lines, you have to also state the parallel lines. OD is parallel to AD. And then A2 is going to be half of O1, which is supposed to give us 27 degrees. So this is because angle at center equals 2 times angle at circumference. So we are done with A2. So C, like I said, ADCB is a cyclic quad, or ABCD is a cyclic quad. So A2, or rather C, is equal to 180 minus A2 because of the opposite. This is 7.2.2 opposite angles of cyclic quadrilateral. So this is 180 minus 27. That should be 153, I think. You will verify for me. And then prove that DA bisects OAB. DA, where is our DA? DA bisects the angle OAB. So to bisect is to cut into 2 equal halves. So basically we are requested to find A1 and prove that A1 is the same thing as the A2 that we found. So that is our job. Our job is to prove that A1 is also 27 degrees. If A1 is 27 and A2 is 27, then DA bisected the angle A. So where might we start with this? So we have O1. Let's see. O1 is the one that gave us A2. Now A2 is the one that gave us C. If it's possible. Okay, A2, by the way, A2 is going to be equal to D1 because because OD and AB are parallel. So D1 and A2 are alternating angles. So D1 is equal to A2, which is 27 degrees because of alternating angles. And I said if you use any one of the parallel line theorems, then you must tell us which lines are parallel. Now, because O is the center, OD is a radius and OA is a radius. So these two are equal. So if they are equal, A1 must be equal to D1, which is equal to 27 degrees. And that is angles opposite equal sides. If that is true, therefore, we've just proven that A1 is equal to A2. So DA bisects OAB. We are done there. We are on the harder ones where we will also have to prove a cyclic quadrilateral at some point. So let's read the statement carefully and draw information from it. They say in the diagram, O is the center of the circle. So if O is the center of the circle, OA OP, these are all radii, right? Even OB is also a radius. So I just want to make a copy, and because this diagram is a little bit complicated, I might mess it up. So we've got OA, OP, and OB. So since OP and OB are equal to each other, B3 is gonna be equal to P1. But we will get there if there's a need. So PB is extended to C. PB is extended to C. AC is drawn. AC, yes. And then PN is a tangent. We are being told that PN is a tangent. So since PN is a tangent, we can apply tan-chord theorem. We can also apply the theorem that says tan perpendicular to radius, or perpendicular to diameter. The tan-chord theorem means that P2 is going to be equal to A1. So A1 is 37 because the chord is PB, not PC. PB is the chord, and this chord subtends A1. So A1 is going to be 37 degrees. But like I said, since this is a diameter, the tangent is perpendicular to the diameter. But not only is this going to be a 90, we do have another 90 degrees here, because a PA is a diameter, and diameters subtend 90 degrees at the circumference. So we've got that as well. Note that we have equal sides, which we said is OA and OB. So it means even B2 is going to be at 37 degrees because those are angles opposite equal sides. So there's going to be a 37 degrees here. Can I just make that clear or visible enough? 37 degrees there. So yeah, let's see where this takes us. They want us to determine, giving reasons, the size of O1. So since A1 is 37, A1 is subtended by PB at the circumference, but PB also subtends O1 at the center. So angle at center is twice angle at circumference. But our job is to first talk about how we got 37 for O1. So 10.1.1. A1 is equal to P2, which is 37 degrees. The reason for this is tan-chord theorem. Now, O1 is twice A1. So 37 times 2, that's going to be 14 plus 60, which is 74. And the reason is angle at center equals 2 times angle at circumference. And then we are done with finding O1. So we know that this is 74. Because this is 74, it is easy to find B3 and P1. P1 and B3 are equal to each other. But even aside from that, since we said the whole angle P is 90 degrees, P1 is going to be 90 minus 37. We can also use that. And whatever P1 is going to be the same as B3. So we are on 10.1.2. We have to prove a cyclic quadrilateral, OACB. OACB. So let's attempt to draw a circle around there. Excuse me, I'm going to delete these here because I want to use that circle or that diagram. I'm going to try to draw a circle. Let me make it orange. So OACB so we've got three ways to prove a cyclic quad. We can try to prove a cyclic quad by proving that the opposite angles of a cyclic quad are supplementary, or we can prove that the exterior angle of a cyclic quad equals to the opposite interior, or we can prove angles in the same segment. Remember, angles in the same segment looks a little bit like this. If I can prove that this angle is equal to that angle, then I've proven a cyclic quad still. Those are all converse methods. So let's see. If we were to prove opposite angles of a cyclic quad, then I would have to take the whole O3 and O2 and C1 and C2. Or I'll have to take A1 and A2 against B1 and B2. That is if I want to use opposite angles. If I want to use exterior angle, then I must use B3 against A1 and A2. Just try to follow along. I'm not yet solving. Or I can use O1, because O1 does seem to be an exterior angle, against C1 and C2. That is if I want to use exterior angles. But if I want to use angles in the same segment, then C1 will go with B2, or I'll have A2 going with O2 like that, or I can have C2 going with A1. See that? Because they are subtended by OB. OB subtends C2, OB subtends A1. Or I'll have to use O3 against B1. And I think O3 against B1 is going to be the easiest one to use, because we can talk about B2 plus B3. B2 plus B3 is equal to 90 degrees because it is subtended by a diameter. So we say these are angles in a semicircle. O3 is already given to us as a 90 degrees. So this implies that B1, because B1 is an angle on the same straight line as B2 and B3, even B1 must be equal to 180. Must be equal to 90. B1 will be equal to 90. And the reason for that, it's because B1 plus B2 plus B3 is 180. But B2 plus B3 is 90. So if I subtract 90, I get a 90. We say this is angles on straight line. So now, what have we just proven? We've proven that O3 is equal to B1, which is equal to 90. We've proven this. I don't need a reason for that. Therefore, OACB is cyclic quad. Now I need a reason for this. Why is this a cyclic quad? It's because I've proven the converse of angles in the same segment. So this is converse angles in same segment. Okay, so that is it. Go back and make sure you re-watch this part until you understand what we are talking about. Slow it down if you have to. And then OC, we have to prove that OC is parallel to PN. 3 ways for now that we can use to prove parallel lines. If I have angles that are in the Z fashion and I prove that they are equal to each other, then it means the lines are parallel. If I've got angles in the F fashion and I prove that these angles will be equal to each other, then I've proven that these lines are parallel. But if I have angles in the U fashion and I prove that this angle plus this one gives us 180, then I've proven co-interior angles are supplementary. So that is what one of those 3 is what we need to use. So let's look at the lines that they are talking about. They said OC. I'm going to use this older diagram. OC is parallel to PN. Remember, we said this is a 90 degrees, and clearly this is going to be a 90 degrees. So that is what we need to do. O1 plus O2 plus O3 is equal to 180, but if I minus O3, O1 plus O2 is 90 degrees. And the reason for that, this is part B. The reason for that is angles on the same straight line. Now that we have that, I have to tell them that P1 and P2 are also 90. P1 plus P2 is also equal to 90, but that is because we've got a tangent and a diameter. So we can say tan perpendicular to diameter. Now, what have we just proved? What have we just seen? POC, which is O1 plus O2, plus OPN, right? So POC plus OPN. In fact, here instead of the O1, O2, we can use POC and OPN. We can change these to POC and OPN. POC plus OPN is equal to 90 plus 90, which is 180 degrees. We have proven angles that are supplementary. So therefore, OC is parallel to PN. We were trying to prove parallel lines, so we will say co-interior angles are supplementary. Or you can just say converse co-interior angles. Okay, so we are done with this one. We can move on to this last one. Looks like a little bit of a complicated diagram, so I'm going to just take a copy of it. So they say in the diagram, PAT is a common tangent of the smaller and the larger circle. We've got a tangent, so we can now think about tan-chord theorem. So A1 is an angle between the tangent and the chord AC and AS. So A1 must be equal to B, and it must also be equal to M1. But even A3, I'm going to put a dot, A3 is a tangent, is an angle between tangent and chord AB and AM. So A3 must be equal to the angle subtended by those chords. which is C and S1. Okay, let's move on. AMB is a diameter. Now that we know that we've got a diameter, it means this is a 90 degrees because AMB subtends a 90 degrees at the circumference. And since we said this is a 90 degrees, this will also have to be a 90 degrees. We already said they are equal to each other. Even that is going to be a 90 degrees. But that makes sense because it's tan perpendicular to diameter of the larger circle with M on the circumference of the smaller circle. ASC and BC are chords of the larger circle, and MS is the chord of the smaller circle. M is the center of the larger circle. It is also given that the length of AM is P units, so AM is P, but M is the center, so this is P, that is also P. So they also say to us that AS is P minus 1, so this is going to be P minus 1 here. SC, they've not said anything about it yet. We don't know if S is the center, or is the midpoint of AC. So let's not assume it. So, and BC is equal to 6 units. BC is going to be our 6 units like that. And then they say name giving reasons 3 angles equal to 90 degrees. Here we are. We've got 3 angles already, right? So we can say angle C equals 90 degrees because it's subtended by a diameter. So that's going to be angle in semicircle. Because I'm referring to one angle, that is why I'm saying angle. But in the other examples, I was saying angles because I was referring to more than one angle combined. So C is equal to 90 degrees. But even A3 is 90 degrees because this is going to be tan perpendicular to diameter. And then this S1 is going to be equal to A3 because of tan chord theorem. So that's 90. And that's going to be tan chord theorem. Okay, so those are 3 examples of 90 degree angles. Give a reason why MS is parallel to BC. Where is MS? MS parallel to BC. Clearly you can see that the corresponding angles are equal. They kind of form an F. So corresponding angles are equal. I'm removing this. So for the second one, we can say corresponding angles are equal. And then they want us to write down the ratio of AS to SC. So this line here is said to be parallel to that one. We know that M is the midpoint of AB. Automatically S becomes the midpoint of AC because of the parallel line and the other midpoint. That is called the midpoint theorem. It was done in grade 10. We revisit it in grade 12, but it's a grade 10 topic where we say if I've got, let me show it to you. If I have a triangle like this and the line that's joining 2 sides like that, then if that line is parallel, so if this is A, B, C, and then this is MN, the theorem says that if MN is parallel to BC and M is the midpoint of AB, then N will also be the midpoint of AC, and better yet, MN is going to be half of BC. So we've got two conclusions. N is the midpoint and MN is half of BC. So that is something that is supposed to have been learnt in grade 10. Let's move on. So if they are asking for the ratio of AS to SC, because S is going to be the midpoint of AS and of AC, then it means this will be equal to that, and the ratio of two equal sides is 1. So the answer is 1. So what we can do is to say that S is midpoint of AC according to the midpoint theorem. We don't need to say M is the midpoint and SM is parallel. We already know that. All right. Then therefore AS is to SC is equal to 1 is to 1. So they are asking us to write down the length of MS. Just like I said, MS will be half of BS, so to write it down, that is going to be BC. AS is going to be half of BC, so it's going to be 3 units. Now they are asking us to calculate the value of P. Let's use the triangle AMS. I'm going to use the triangle AMS. Remember, there's a P here, there's a P minus 1 here, and there's a 3 there. So that's going to be, according to Pythagoras, AM squared is equal to, because there's a 90 degrees here, is equal to AS squared plus SM squared. And then your reason is Pythagoras. So AM is P squared. This one is P minus 1 squared. And then 3 squared. Right? We can go ahead and try to solve this. This is going to be P squared is equal to P minus 1 squared is P squared minus 2P plus 1. And then 3 squared is 9. So the P's will cancel. If I take 2P to the other side, it becomes positive. And this is 1 plus 9, which is 10. If you divide by 2, P is 5 units. Now, why did these P squared disappear? Because if I take the P squared this side, it becomes minus. So P squared minus P squared is 0. And then 2P, the negative 2P taken to the other side becomes a positive 2P. And we just proved that P is 5. We have now come to the end of this lesson. These were the few problems that I wanted us to go over.